Okay, so once again, welcome back. Okay, so now we are in the second part of the module 2. Okay, so in the module 1, what we have discussed is the MOSFET continuation, what we have left out in first module. Okay, so you have discussed single stage MOS amplifiers, MOSFET internal capacitances and high frequency model and frequency response. Okay, so low frequency and high frequency response we have seen. So in the second part, there is a small topic which is about oscillators. Okay, so this is about the applications of now a transistor part it will be. Okay, so oscillator you will be using, that part I will try to explain where it is used and what are the different types of oscillators and all we will discuss. And majorly in the syllabus you have the phase shift and LC and crystal oscillators, so that we try to focus. Okay, so today session, small time is that I will try to cover the introduction to oscillators. Okay, so very attentive, so very important to understand the remaining sessions on oscillators. So in the design of electronic systems, the need frequently arises for signals having prescribed standard waveforms. For example, sinusoidal, square, triangular, pulse. Okay, so these standard waveforms are used. For example, if you take a clock, right, a digital clock, so it will be continuously oscillating with pulse, right? So like this. So even in your digital signals, you have seen 0 1 0 1, it is continuously, right? So even your computers synchronization, something is there in your settings, right? So most even you have observed, if your mobile time is different, and then if you install WhatsApp, it will say WhatsApp could not access the data because time is not matching with your device. That is synchronization, and it perfectly happens with this waveforms. Okay, back in the back it will be working. Okay, so that is called as standard waveforms. Some applications, some will be required. Okay, so normal computers and all, we will be using square or pulse waveforms. Triangulars also used in some other applications, sinusoidal, like that. Okay, so these are standard waveforms and they are very much used. Okay, so what are that applications? We'll try to focus. System in which standard signals are required are computer. As I told you, first thing is computer and another is control systems. That is our another subject, right? So control system is a very big subject. Okay, so nuclear control, satellite control. Okay, so automobile control or a automation. Okay, so everywhere control system is there and it depends on the clock. Okay, it requires a standard signals. Okay, so even we are studying now time response of the first order, second order systems, we are using their standard signals, right? The square, okay, or a standard step input, all these things. Okay, so same way sinusoidal, all these things also used. Okay, so these are the two applications where clock pulses are needed. For many other things are there, among other things, for timing purpose we'll use. Okay, in control systems and computer. So computer clock is it is continuously running, right? So it will synchronize with the global clock. Okay, so in India it will show you New Delhi, Mumbai, Kolkata, like that, right? Even when I am sending the Zoom meeting details, it will show you. Okay, that means Zoom cloud server time, your time, everything it will match. Okay, so that is called as timing. For that standard signals are required. Second application area is communication systems, right? You are using the data, 4G, 5G, whatever, right? And mobile, cellular mobile, where signals of a variety of waveforms are utilized as information carriers. So I will be talking through now online, right? So my data is sent over some channel, right? Wirelessly, you are sitting in a home and you are listening. My information is carried by one of these signals, sinusoidal, square, triangular, we don't know background how it is working. So that's how, if you really work in such industries, you will come to know, right, what waveforms will be working, right? So you'll be learning about more about in communication system in higher semesters. Okay, so that is another application of these standard signals. And third most important thing is the test and measurement systems. So your function generators, CROs, right? Or even if you have seen in the TVs, when if they show NASA or the ISRO, okay, there are big devices, instruments, they will be sitting, right? Measurement instruments, right? So all these things require signals, standard signals required. Again, of a variety of waveforms are employed for testing and characterizing electronic devices and circuits. Okay, so your lab equipments, okay, so you will be seeing many lab equipments and all, they will be tested, right? So for that again you require the standard waveforms. I have started my introduction from here. From here I am touching to oscillators. Okay, so standard waveforms are necessary and their applications are in computer control systems, communication systems, test and measurement systems. Okay, so now there are two ways, two distinctly different approaches for the generation of these standard signals. Okay, two distinct, not in a same approach, two distinct different approaches are there in generation of the sinusoids, perhaps the most commonly used of the standard waveforms. Okay, so what are those? There are two techniques. First approach employs a positive feedback loop in your amplifier. Okay, so far you have discussed. So again in the third module we will be discussing regarding negative feedback loop. Negative feedback loop, when we use, we call that as a feedback amplifiers. Okay, and now amplifier. So in the forward path you will be having the amplifier with its gain A, and in the feedback also you are using, right, control system and all you have seen. So you are using a feedback. So that feedback, if you use a positive feedback, then it becomes a generating a signal. Okay, so like that. So here plus minus I am writing in the summing point, right? So if you write that plus, it is a positive feedback. If you write minus there, it is negative feedback. Okay, so we are employing such positive feedback loop in this case. Okay, so what it consists of? It consists of an amplifier in the forward loop, and in the feedback path you can have different elements here. Combination of R and C you can have. We call that as RC oscillators. You can have LC, okay, inductor and capacitor combination. We call it as tuned oscillators, or it is Hartley, Colpitts oscillators are there. Okay, and then also crystal, also you can, piezoelectric crystal, which is used in your watches and all, that also can be used. If you use that, we call it as crystal oscillators. We'll be seeing that all category. Okay, so that we use it as a frequency selective network. In the frequency selective network, we'll be using this RC, LC or crystal as the combination along with the amplifier, and this together we call it as the positive feedback loop. This forms a loop, right? In signal flow graph and all, you know what is loop. Starting from same point, goes through the loop and comes back to same. So in this forward path, you have the amplifier now, whatever we discussed previously, MOSFET, CS amplifier, common drain amplifier, all these things. And in the negative path, feedback path, you will be having these frequency selective network. It may be any. If you have RC combination, we call RC oscillators. If you have LC combination, we call LC oscillator. If you have a crystal, we call it as crystal oscillators, that we see. Okay, and next, the amplitude of the generated sine waves is limited here or set using a non-linear mechanism. So normally your amplifier is a non-linear one. Okay, so which will give you 180-degree phase shift output, right? Amplifier. So non-linear mechanism is there and implemented either with a separate circuit or using the non-linearities of the amplifying device itself. The device itself is having some non-linearities. In spite of these challenges, these circuits which generate sine waves utilizing resonance phenomena. Resonance we have learned in network theory. So using that phenomena, it will generate the sine waves. Okay, in the non-linearities of the device itself, it will generate the sine waves utilizing resonance phenomena are called as oscillators, or it is called as linear oscillators. Okay, so we are discussing the first approach in generation of sinusoidal or standard waveforms. Okay, that first approach is our linear oscillators using a positive feedback loop mechanism. We'll continue. So what is the basic? The name clearly distinguishes them from the circuits that generate sinusoids by way of the second approach. Second approach is called as a wave shaping circuits. Okay, so the second, in these circuits, a sine wave is obtained by appropriately shaping a triangular waveform. From triangular waveform, you will give a shape. Okay, such circuits we call as wave shaping circuits. Okay, so this is there in your book, but we are not discussing in our syllabus this wave shaping circuits. We are discussing oscillators. Okay, then the circuits that generate other kind of waves like square, okay, triangular. So whatever oscillators we have used, it is using sinusoidal wave. It will generate sinusoidal wave. In that, two approaches. One is oscillator, linear oscillators. Another is wave shaping circuits. Now there are circuits that generate other waveforms like square, triangular, pulse. You have seen in function generator, right? So that waveforms are called as non-linear oscillators. We generate that oscillators, we call it as non-linear oscillators, or we call also function generators. That's why we call this name. In your ED lab you have seen signal generator or a function generator name we will use, which is nothing but it will give you different waveforms there, right? Sine wave, square wave, triangular wave, pulse, everything. Okay.
So depend upon the input, we get the output waveforms. No. So function generator is just an example for getting different kinds of wave.
Yeah, it is one application. Okay, so it is a function generator. In that, the devices are there, electronic devices are there, combination. Okay, so the
So, but how is
square.
it related to oscillators?
Yeah, pardon.
How is it related to oscillations?
I will tell you. The still I have not introduced the oscillators, how the principle and all. I will tell you. Oscillator means the device itself will produce the waveforms by using the nonlinear mechanism in the amplifier. Okay, and along with we will use a positive feedback loop. Okay, so because of that it will produce the oscillations. First I am giving these different types of circuits. Okay, applications of transistors. First one I gave you linear oscillators. Second I told you wave shaping circuits, this we are not discussing. And then non-linear oscillators, also called as function generators. How this will be generated, okay, how it will, that employs circuit. Okay, circuit building blocks known as multivibrators. Something called as multivibrators will be using. And there are three types of multivibrators are there: bistable, astable, and the monostable. Okay, so this we will discuss in the module 4 and 5, where we are discussing op-amp, and these are the op-amp applications. Okay, so operational amplifier we will use. Using that we will discuss this multivibrator. Since I am giving a overall picture of the next coming portions. Okay, so linear oscillators and non-linear oscillators, two kinds you have in oscillators. So now our focus should be on generating the sinusoidal waves, nothing but linear oscillators. Okay, so before that, what is its basic principle? So basic principle of sinusoidal oscillator. So now we will get to know so how exactly it will produce the oscillations. Okay, even in next we will be using these applications in our HDL lab and all. Okay, so like that these waveforms are continuously generated, right? In the even your computer, your mobile, continuously it is creating some pulses. How it is going to do? Some devices are there. The basic structure of a sinusoidal oscillator consists of an amplifier. It will have amplifier 1. So amplifier means, just I am showing a block diagram. It may be common source amplifier, common drain, any. So that amplifier means it will have hundreds of MOSFET also, not only one. Okay, so it's having a MOSFET is the main building block, along with resistor, capacitors, everything is there. That is the amplifier block. And then in the feedback path you have a frequency selective network. Okay, so here we are doing the design. Based on that we have different types of oscillator. Amplifier part you have already learned. Now we have to focus on frequency selective network. So it is connected in a positive feedback loop. Positive feedback means at this summing point it should be plus sign. See here, if you have a minus sign, we call that as feedback amplifiers. That is our module 3 topic. Okay, now we are discussing plus sign, which is a positive feedback loop. Because of that, so you'll see the oscillations. Okay, so we'll see that. Okay, next, although in an actual oscillator circuit no input signal will be present. See here, so function generator itself will produce the waveforms. It does not require any input signal, but still we include an input signal here to help explain the principle of operation. I have shown you some source here, XS, right? It is just to show you, complete the explain the principle of operation, or else the amplifier non-linearities along with this only it will produce the waveforms. Okay, so in the ocean, if you have gone to beaches and all, you have observed there, right? So is there anything you are doing to create the waves, right? If you go mid of the sea, you will not see any waves, right? It will be a still water. But when it comes to the near to the beach shore, so you will see the waves, right? Different waves. How it is happening? Naturally, right? Because of its internal mechanism. The same way here, amplifier non-linearities, and along with the positive feedback. So it will create the oscillations, and these oscillations we will be using in different applications. Okay. Okay. So this I will explain you in the next class. Maybe time is short. Okay. So I will continue this same discussion in the next section.